All right, gotten several emails and comments and concerns, so I thought I'm going to take just a quick stab at trying to make this make sense, at least a somewhat roundabout effort. So statistical inference. Okay, so what I want you to do is I want you to think for a second about an argument you had with someone. If you're married, it's kind of easy to imagine, and if you've been dating someone for a while, you kind of draw back from those experiences. And I want you to ask you a question. Why did you argue? Right? What was, when all said and done, when everything was finished, what caused the argument to begin? Generally speaking, at least from my experience, whenever I've had an argument, it's because somebody thought I was wrong. Right? So here I go in life, and I have an opinion, and I'm doing my thing, and somebody comes and corrects me and says, you know what, I think what you're doing is wrong. Well, when someone says that, what's your first reaction? Your first thought is to kind of go, well, no, I'm not. And they go, yes, you are. Right? Instead of going no and yes back and forth, you actually go out and you collect evidence, you collect data, you cite facts, you go back to previous things that have been said. You make an effort to sort of change the other person's opinion, or they're making an effort to change your opinion. Okay. So in statistical inference, that's what we're talking about. Why do we gather data? Why do we care? Well, we care because we think something's different. Or we care because we really don't know what's going on, and we're trying to find out what is going on in the real world around us. Okay? So, in the idea of statistical inference, I go out and I gather data, and I expect, let me kind of throw a picture up of a normal model. So out in the real world, when I gather data, here's what I expect to see. I expect there to be a middle. I expect there to be some sort of central value that things sort of tend to be around. And I expect there to be things that are a little bit above it and things to be a little bit below it. You know, if I go fishing, for example, I expect the average trout to be about 10 inches. And I might be lucky and catch the 12-incher, the footer, the one that I want to brag about, or I might feel kind of bad and I might get the 6-incher, right? But I have this sort of expectation of what is expected in the world around me. And so when I gather data, I'm comparing it based on that expectation. Okay, so in statistics, what we get excited about is, well, first off, what I don't get excited about is when I expect something to change, I go out and collect data and I don't find any change. I think that's boring, and why did I bother to collect data? But when I go collect my data, what if I find that instead of having a little bit above and a little bit below and most of it in the middle, what if I find that it's all above what I thought? Or what if I find it's all below what I thought? Okay, so it's when our sample happens to be one of these extreme values, either above it somewhere or below it somewhere, I get excited and I think, wow, I thought something was different. I went and collected data and it in fact was different. Okay, now mathematically what we're talking about is this idea of statistical significance. It's when I look at my sample, how likely is that sample supposed to show up if what I'm assuming is happening is happening? Okay, kind of go back to that normal curve I was talking about. So if I expect this, and I get a sample that shows up here, that it's way outside of my expectations, so far out of my expectations, that I would expect it to only show up 1 in 20 or even 1 in 100, then I would call that statistically significant. Okay, now let me just kind of clarify here. It's not one or it's not both. It's one or the other. Before you gather data, you kind of have to decide what are you going to determine as significant or not. Do you think 5% of the time or the 0.05 level is statistically significant, or is the 1% level? To kind of hit home with a point here, those that are moms, think back to when you gave birth to your first kid, and dads kind of think back to second, and those if you never had to deal with this, then that's fine. When the baby's first born, immediately what happens? They put a wristband on them. They put a wristband on the kid, they put a wristband on the mom. Now that might not seem silly now, but there was a time when they wouldn't do that, when they weren't doing that. And so you got to ask yourself, well, why not? Right? What caused them to decide to put the wristband on the baby and the mom right after the birth? Why didn't they wait a little bit, or why did they have that process in place? And what happened is babies on accident were going home with the wrong family, and they weren't finding out about this, and some of them were never finding out about this ever. And those that did find out didn't find out for quite a while. Now that's kind of a scary thought, to think you gave birth to this child and it's not what you have at home is not the child that you gave birth to, right? So they have this process in place that they only want to have the accidents occur a certain amount of time. So their level of significance is a lot stricter than the 0.01%. They might have, instead of 1 of 100, they want 1 in 1,000 or 1 in 10,000 accidents for that to occur, right? So they're a lot more cautious with that. But things like medical trials, well, I guess maybe that's something that they want to be more stringent with as well. But other types of data collection processes, maybe they're a little lax on that, and so that's where the 5% level comes in, or 1 in 20 they consider to be statistically significant. Okay, so here's kind of 2 situations, and we'll kind of talk through whether or not we feel that they are statistically significant or not. Case 1, you've got a baseball team with the worst record out there, and they play a team and they win. But the team they played is at its best record. Is that something that we go, oh my, is that statistically significant? Okay. And the other scenario is looking at the average temperatures around the world from 2001 to 2012. The last 12 out of the 14 years are the hottest since 1880. Is that statistically significant? Okay, so let's kind of, now I'm going to post the answer up here just because it's fun. Why not? But I mean, you have this. When we're talking about the baseball team, are we excited that they win? Sure. But is it something that we think that there's something else going on when the worst team beats the first place team? Not really. I mean, we're surprised by it, but if sports were a guarantee, if I knew for a fact that the worst team was always going to lose against the best team, no one would make any money off that, right? And technically, teams can, the bad team can have a really good day, and the good team can have a really bad day. And so that's not enough of a randomness. It's not enough of a coincidence for us to get excited. However, 12 of the hottest years occurring in the past 12 years, as compared to, let me kind of go back here, as I kind of missed this detail, that they recorded temperatures since 1880. So you're talking 120 years of data, and the last 12 happen to have been the hottest, or 12 of the 14 are the hottest years on record. Is that a significance? And you got to think that if you're looking at 120 years, the fact that these 12 years grouped are the hottest, that's weird. There must be something going on, right? And this is where this whole global warming trend comes in. That we're, scientists and other such are starting to look at this and go, oh, wow, this is not random. There is something going on in the environment, right? My job is not to convince you that global warming is real or not, but that's the evidence pointing to that there's a concern is real, and maybe not we should do something about it. Okay, read this to you. Researcher conducts a double-blind experiment that tests whether or not the new herbal formula is effective in preventing colds. During a 3-month period, the 100 randomly selected people in the treatment group take the herbal formula, while 100 randomly selected people in the control group take a placebo. Now, let me kind of pause it real quick and kind of clarify this. So they grabbed 200 people. 100 of them actually got a drug, actually got something in their water. The placebo group got like a sugar pill, or got flavored water that didn't have anything real in it, right? And what would we expect to see? If this drug is doing nothing, I'd expect the same number of people that using that whole positive mental attitude, I'd expect the same number of people in the drug group as the placebo group to go, hey, I'm better, right? However, if it is significantly different, I'd expect there to be much larger group that says, wow, this herbal formula is making a difference. All right, so we get to the results, and the results show that 30 of the treatment group get colds compared to 32 in the control group. Is this evidence that the formula is preventing colds? Because we have 32 in the control got a cold, and only 30. So clearly that means it got better, 2 people, but is 2 people enough to get excited? Okay, and the answer is not really. You know, we expect a certain percent of any group of people to get a cold, and the control group had 32% show up, but 30 is just so close, right? But that kind of brings up a question. There's got to be a number. So if 30 compared to 32 is just really close, what if it was 29? What if it was 28? What if it was, right? There's got to be a number that at one point we go, yeah, that's really not that significant. And then the other number we go, that's actually very significant. Like if I said that only 5 out of the 100 in the herbal group got a cold, we'd get excited because then we're like, oh wow, this herbal formula is actually preventing people from getting a cold. But maybe not 5, maybe. So there's just got to be this magic number where we think something interesting has happened versus not. Okay. That brings us to something called a margin of error and confidence interval. Now, I'm going to be flat out honest with you. I wish I was around the day they came up with the names of these things. I'm going to pull up another file and illustrate a point here. Okay, so let me kind of throw this question at you, and then we'll go back to what our book is saying. Suppose I give you a jar of pennies, and I want you to estimate how much is in the jar. What would you do? Right? You can't pour it out, but you might look at a corner and sort of count, sort of estimate what you might want to go about doing that. Okay, so when we do a confidence interval, we have to have something called a point estimate. And a point estimate is a count. So I might count how many pennies I can physically see. And that estimate is not what I'm going to say the actual population is. I'm not going to say this is what I think is going on. This is what I can see. So there's got to be a wiggle room. There's got to be a plus or minus around this point estimate that allows me to predict what's actually in the jar, predict what the actual population is. And so around this point estimate, we introduce something called a confidence interval. And this is used just to, quite frankly, estimate what's going on in the population. I may or may not know much. The formula is pretty straightforward. I take this point estimate, can I go back here? I take this point estimate, which is the statistic, and I add into it this idea called a margin of error, how much off we might see this. You might see something like this in a presidential election where they'll say, we predict the candidate's ahead in the polls by 3%, by a margin of error of 3%. So whatever number they say could be plus or minus 3 on top of that. Now, the margin of error, I really wish I was in the meeting that day when they came up with a name for this. It just sounds like error, sounds like someone made a mistake. But it's a measure of how accurate we believe the estimate is. So it's that point estimate with some wiggle room attached to it. And the idea behind a margin of error is that the smaller it is, the more precise our estimate is of the population. So we like small margins of error. Margin of error plus or minus, if you ask me what do I have to make on the final to get an A in this class, you would like me to say things like, oh, we need to make a 90 plus or minus 2. Right? That means you can make an 88 or a 92. You need to make a 90 plus or minus 10. So anywhere from an 80 to 100 will get you there. Right? So with margin of error, we like more precise estimates. And it's got this nice fancy formula that we don't really cover necessarily because we're not really a statistics course. But here's an interesting thought experiment just to kind of help wrap your head around what a margin of error does. What if I asked you to guess my age within 10 years? You've seen my picture, you've heard my voice, you probably have no idea how old I am, but how confident would you be if I gave you this 10-year range? I would think a lot of us would be like, I could probably do it. I could probably get it right within 10 years. Okay, what if I said 5 years? Now notice, our confidence is a little less. I'm less confident with a smaller target. What if I do it within 1 year? I can guess. I'm not confident. Not at all. Okay? Same idea, but let's talk about the basketball. So let's say I'm shooting a basket at a wading pool. I got a basketball and I'm trying to get it inside the wading pool. How confident are we could do that? Well, pretty confident, right? Could pretty much do that. What if I give you a very large trash can instead of a pool? Notice how your confidence decreases as the target gets smaller? You're not as confident anymore with that. And then what if I were at a carnival and I say, oh, you gotta hit a basket? Feels like they're cheating there, right? But your confidence gets way smaller with a very tiny target. Okay, so hopefully what happened as the interval got smaller, the lower the confidence, the smaller the interval. Okay. All right. The confidence level, so what we'll typically say is the 95% confidence level. Doesn't mean I believe I'm right 95% of the time. It actually means that I will be able to predict, or I will have the actual population number within my estimate that percent of the time. So it's a measure of the success rate, not a measure of confidence, which I know sounds really confusing. A confidence level is not a statement about how accurate I believe I am. It's a statement of all the samples of this same size, I'm actually going to have the population number in my interval. Okay, so this is a very rough, I actually feel bad showing you this. In statistics, we do a much better job of teaching about margin of error, but for our course, this is a very rough estimate. Okay, there's a lot more formula involved in this, but the idea that on a 95% confidence level, the margin of error we're going to be approximating using 1 over the square root of n. Square root of n refers to the sample size. So if my sample size was 100, then the square root of 100 would be 10, so my margin of error would be 1/10, 1 over 10. If my sample size was 25, my square root of 25 is 5, so my margin of error would be about 1/5. Okay, so again, it's that wiggle room around our point estimate that we would be using to measure that. Okay, so in this case, say we're given some information about unemployment. We're told that 3,420 people are unemployed out of 60,000. Give the actual population unemployment rate, because there's clearly more than 60,000 people in the United States alone or in the world. So what would we estimate the actual population unemployment rate to be? So in this case, I take, first I need to figure out my point estimate. So I take the 3,420 divided by the 60,000, so I get this point estimate of about 5.7%, or 0.057. And then I want to calculate my margin of error, which is 1 over the square root of the sample size, so I get this number here. And so when I calculate the actual confidence level, I would go plus or minus that. So let me kind of pull up something I can write on. Okay, so I've got this point estimate of 0.057. My confidence level, so we got the margin of error of 0.004. So my confidence level is going to be this number, the 0.057, the point estimate minus the margin of error, and the point estimate plus the margin of error. Okay, so I would estimate then that the actual population unemployment rate, not the 60,000, I'm talking on a larger scale, I would expect it to be somewhere between 5.3% and 6.1%. And that's about as accurate as I can be, simply because I only talked to 60,000 people, because I only had the sample of 60,000 to base it off of. If I talked to more people, I would have a smaller window. Right? If I talk to less people, I'd have a larger window. That's kind of how that relationship goes. Okay, so what is a hypothesis test? It is a process that allows us to determine whether or not something is statistically significant. Okay? And again, statistically significant refers back to that 5% or that 1%. Most of the time we're going to stick with 5%. And it's how often would we expect this particular sample to show up, because again, we expect a little bit above, a little bit below, but we saw something way above or way below, and I don't think that's random. I think that's because something else is going on. Okay, so yeah, kind of emphasizing that. When I look at my data, is my data something boring in the middle of the graph, or is it something more extreme like on the edge? Because on the edge means that what I think is going on is not really what's going on. There's evidence that something else is happening. Okay. And so these calculations, we refer to a test statistic, and it tells us how far off from the mean we'd expect something like this given a certain situation. Okay. Now, when we do a hypothesis test, it sounds weird, but we have something called a null statement and an alternative statement. The null statement is, what do we start off thinking, right? I suspect something else is going on. So kind of go back to that argument I talked about earlier. Before anyone tried to argue with you, you had your own way of doing things. And then someone came in and told you were wrong, right? So they looked at what you were doing and they had this alternative thinking. Maybe they're wrong. I'm going to give them evidence that they are wrong, and hopefully I can convince them. Right? So when we do a hypothesis test, we look at what's called the null and alternative, and our null statement is defined by what do we want to gather evidence for, but let's assume it's not there. And that's our null. It's supposing the effect is not present, and the alternative is to see if the data suggests there's evidence against that statement, against the supposition. So a classic example is a murder trial. Right? When someone goes up for a murder trial, what do we assume? We assume they are innocent until proven guilty. So our null statement is they are innocent. Our alternative is that they must be guilty, right? And then we sit there and we hear all this evidence of why they are guilty. Okay? Okay, so going back to our textbook then, we have a null and alternative. And the null, again, is assuming that whatever we're investigating is not present. And the alternative is why I would like to, what am I trying to show? What am I trying to gather evidence for? But it's in terms of the null. So either I think it's bigger than what the null is, or smaller than, or it's not equal to. But it's all defined in terms of that null hypothesis. Okay. When we test the hypothesis, we have one of two outcomes. Either we find enough evidence and we reject the null because we have evidence to support the hypothesis, or we not reject, or we fail to reject the null because we lack evidence to support the alternative hypothesis. For the married folk in the room, that means you never have to admit you're wrong. You just have to say there's not enough evidence to support your statement yet. By the way, don't try that one at home. That will get you in trouble. Okay, so again, if the sample is not rare enough, if it's not significant enough, we would say that we fail to reject the null. There's not enough evidence to support the alternative hypothesis. All right, so let's see. Describe two possible outcomes of a hypothesis test concerning a gender choice product. Okay, so that means out in the real world you have some pill or some thing that determines the gender of your baby. Let's see, so we would expect then for your null that the product doesn't make a difference at all. So the likelihood of me having, well, in this case we'll say girl is 50-50. You know, half the time it should be girl, half the time it should be boy. And if this product is in fact adjusting that, if it's manipulating that, then I'd expect it to be greater than 50%. So if I've got some magic pill or some magic little elixir that's going to give me a stronger likelihood of having a girl, then the probability of me having a girl should be greater than 50%. Okay. Let me read this out here. We can reject the null and accept the alternative. Ooh, I hate the word accept. That's another statistics thing in me coming out. So if the evidence doesn't support in other words, if I go conduct this evidence and it turns out to be something that shows up 1 in 20 times or 5% or less, then I would say that's evidence against the null, and we'd go ahead and reject it. Or if my sample is very boring and it's something that would show up more than 5% of the time, so 80% of the time I'd expect to see my sample like this, then we would decide to fail to reject the null, that there's not enough evidence to support it. So it's either one or the other. It either supports it or it doesn't, and we either reject or we fail to reject the null. One of those two decisions. Okay. And then we talk about evidence, the likelihood of certain things. So if we say it's the 5% mark, so 1 in 20 we would expect to see something like this, that's a moderate amount of evidence to reject the null. But 1 in 100 is strong evidence. So the rarer our sample is, the more it gives evidence for the alternative, and the more common it is, different upper percentile of seeing something, there wouldn't be any evidence against the alternative at all. Okay. County health official believes that the mean birth weight of male babies at a local hospital is greater than the national average of 3.39. Okay, so we think the national average is 3.39. So all null is that it's 3.39. I think it's bigger than that. I think my hospital's got really large kids, and so I'm gonna go look at my sample and see, does my sample support evidence that it's bigger than 3.39, or, as the null would say, that we're stuck with it equaling 3.39. So I go out and I sample 145 male babies, and 145 of them have a mean birth weight of 3.61. Okay. So the question is, how likely would I see 3.6? So in other words, you take all 145 babies, add them up, add their weights up, and then divide by 145. How likely is it that I'm going to see 3.61, given that I expect to see 3.39? I mean, so in other words, I would expect to see, around 3.39. I'd expect to see a couple of really heavy babies. I'd expect to see a couple of light babies. But the fact that I got 145 of them to average out to something much bigger than 3.39, what does that evidence suggest? Okay, so let's see, formulate the null and alternative, then discuss whether this is evidence to reject or fail to reject the null. Okay, so first we kind of do what I said. So our null is that it equals 3.39, and that the alternative is that it's bigger. Okay. Then we look at that 3.61. We're told that the likelihood of me getting 3.61, assuming that it was 3.39, is only going to happen about 3%, or about 0.03. Okay. Keep in mind, 0.05 is moderate evidence. 0.01 is strong evidence. Right? So what do we have here? We've got moderate evidence for rejecting the null. In other words, I think the babies are heavier. The likelihood of me getting 145 of them to be 3.61 when I expect to see 3.39, really small. About 3% of the time I would expect to see something like that. So I think there's evidence to suggest that it's different, that the babies are in fact heavier. Okay, so hopefully having me talk through this helped. A little bit better than reading, hopefully. If you still find you have questions about margin of error, confidence intervals, or hypothesis tests, please feel free to email me them. I teach this for statistics, so it's really hard on my end to go, all right, they don't know about this, or they should know about, it's kind of hard to balance out the knows from the not knows. So I tried to do that with you. But if you have any more questions about it, feel free to email me, and then I hopefully can adjust this and make this lecture a little more interesting for you.